control is about disturbances. So we need to handle disturbances. I now handle the first disturbance of this lecture. The disturbance we are not going to talk about today, but we are going to talk about the error. So we measure the error of the position of the vehicle to the reference trajectory, and we correct this using we have a further disturbance. Okay, no problem. Maybe this. Okay. I think now we have everything. So this is the steering angle to get to the reference trajectory. What can we do? We can use classical control called also PID to minimize the error between the vehicle position and the reference trajectory. But it's like drilling a hole in the flow of the vehicle and looking on the lane and trying to see the lane and to follow it. This is the classical control. In predictive control, we look outside of the windshield, and we need not to drive to the tree. We need to drive on the lane, but not on the block lane, on the free lane. This is a very short introduction into control, and we look now at a sketch of this. So here is the reference trajectory we need to follow. We use a model to predict the future trajectory of our system. We need to minimize the error between them. We use a control input to minimize this error. So we predict inside a window we call prediction horizon, and we minimize the control action inside a window we call control horizon. So this is, I hope the computer science students now understand something about control. And if you look at it, it was planning and control. Control is about a feedback. We conduct our control algorithm at every sample time. It is an embedded control. So to get control out of our planning, we need to execute it at every sample time. And now how we formulate this mathematically, it is an optimization problem, which we solve at each sample time. So we have an objective function and constraints. In the objective function, we minimize the error and the control action. And in the constraints, we take care of the model, of the state, and input constraints. After solving this optimization problem, we get a sequence of control actions, and we apply only the first one and repeat our optimization at every sample time, again and again and again. This was the very short introduction into model predictive control, and now we get to the network thinking. So I will introduce some examples to get you into the network thinking. So something you experienced or observed, especially in the post-COVID time, two pedestrians walk towards each other. They try to avoid each other once, twice, but maybe they move to the same direction, and somehow they resolve this. But think of they may collide with each other, and how is it if we extend this to n pedestrians? I observed this in Japan at the Shibuya crossing in Tokyo. It's amazing to observe people there crossing the Shibuya crossing. I'm sure it's not the only one in the world where it is crowded. So what is happening here? We want to understand this. Now I would like you to be active in this presentation and solve this mathematical problem. Choose a number between 0 and 100, and the winner of you is going to be the closest to the half of the average of everybody. If you know this, just think about the nice weather outside. If you don't know this game, try to solve it. So maybe there is a price at Bassam, you can grab a coffee there at 4 p.m. I see you thinking. So grab a number and keep in your mind. Now we get to the solution. So most of people don't understand, or some of the people, not most, some of people don't understand and say anything, something between 0 and 100.
Professor,
Why? I'm explaining this.
my guess would be that if I take a lot of averages from different groups, these averages follow a specific distribution, if I remember well. I do not remember which distribution. I think the normal distribution or the uniform distribution. So probably I'm gonna win known this distribution if I know which is the likely number, the more likely number to achieve. I think this is an approach to solve this problem, statistically wise. But
You are drifting, I'll show you. So some of people think, okay, they look at the first line, something between 0 and 100, they say anything. And I am saying the winner is going to be the closest to half of the average. Some of people think, average of something between 0 and 100 is going to be 50. I'm going to say 50. And some people are a little bit smarter and go further and say, we are looking for the half of the average. So the average is going to be 50, the half is 25. The majority of the people will say 25. But the solution is
26.
no, 12.5, because the majority will say 25. So the solution is 12.5. We are looking for the half of the average. So I conducted this experiment many times. It depends on the group size. You get every time something close to 12.5. If people understand the game. And what I want to say with this game is that the decision quality of individual, of everybody of you, is affected by the decision of others. If we now repeat the game, you understood the game, maybe you will say again 12.5, but it's going to be the half, and so on. And at the end of the day, we will converge to 0, which is called the Nash equilibrium in game theory. This is not going to be a talk about game theory, it's not the motivation for the network thinking. Where does the name beauty contest game comes from? Back in the days, there were some games in newsletter, and they were telling people, here are some figures, choose your favorite character, choose the favorite character by the majority, not your favorite character, and you're going to win if you belong to the majority. So you have to predict what the majority is going to choose. And you can compare the same thing also with stock market. So the message of this is the decision of a system affects the decisions of the other systems. And now we get to some more technical details. So in general, we talk about network control systems. In some domains, we call them connected. They have somehow communication. They consist of interacting systems, and they should contribute in general to better perception and decision making. While networking a system, we have many challenges arising from computation time and communication, and also from mixing the system with humans. So we will get issues with feasibility and quality. I show you now 2 examples, one from perception, one from decision making. From perception, assume this vehicle is going to drive in this direction, and this vehicle in this direction, and this vehicle is standing. This pedestrian is going to cross the street, but the sensors of vehicle 1 will not be able to detect the pedestrian. So 3 detects and send to 1, take care, there's a pedestrian going to cross the street. The typical example in decision-making is the intersection. So vehicles should cross the intersection efficiently and safely. And for the safety, they need to coordinate. So in my group, we focus on 3 levels of research. One is the methods. So we try to reduce the computation time and communication of such a system to get it in real time and to deal with the mixed system. And our goal is to enhance feasibility and quality. So feasibility means we get a solution in real time, and quality is also, some people say, optimality of the solution we get. We apply this and solve the problems using optimization techniques, and we have several applications, and we apply this in real-time experiments using our scale model vehicles, which I'm going to show during this presentation. So this is our classification of LCS. I say it, don't worry if you cannot read it. So we classify it into homogeneous and heterogeneous dynamic. In homogeneous, we take care about dynamically decoupled systems. And the coupling is happening in the optimization, in the objective function, or in the constraints. And in this domain, we look at networked MPC. And according to Professor Lunze from Germany, he distinguishes between centralized, distributed, and decentralized. So we focus on decentralized, and for this, there are 2 ways, cooperative or non-cooperative. And we look at the algorithm level at sequential or parallel solutions or priority-based. So this was general view. Don't worry if you didn't get every term. I'm going to tell you the specific parts now. So remember our MPC formulation, it's an optimization problem of objective function and constraints. And now we have the network systems. So we get the connection of the systems in the objective function or in the constraints. And using coupling functions, coupling constraints between agents or between agents and passive agents. What is the advantage of this formulation? We can deal with the action of other agents with respect to their future intentions, because we have MPC, while making decisions of the agent's own control actions. And how we can formulate this problem now to solve it? We can formulate a centralized optimization problem. So here's an example with 4 agents, and we have a center which collects data from all agents. So the red edges are the couplings between the agents, and the black are the communication edges. So we get all information at center, solve a big optimization problem, and send the control actions to the agents back. They will implement them, and we repeat this at every time step. As you may imagine, this will not be applicable in practice because of the high computation time of the network system and because of the safety hazards we have here to deal with a single point of failure. Nonetheless, we implemented as a benchmark for comparing different distributed MPC strategies, and now I'm going to talk about them. So I start with the cooperative distributed MPC. In cooperative distributed MPC, we decompose the CMPC into smaller optimization problems. Each agent formulates a centralized optimization problem for itself and its neighbors. So for example, in 1, we are going to solve the optimization problems of 1, 2, and 4, but we are going only to apply the solution of 1. In 2, we are going to solve the whole optimization problem, and we are going only to apply our. So that means we compute hypothetical plans of our neighbors. What is the problem with this? The prediction consistency. It means that the predictions used or computed in the optimization problem of an agent I at a time instant t, or an agent j coincide with the predictions computed by agent j itself at the same time instant. In general words, this means at a time instant, what I think about you, you think about yourself. This is what we want to achieve. And this is a very important property in the network system. If we cannot satisfy it, we cannot guarantee any stability and feasibility of our system. Cooperative DMPC doesn't satisfy it, exception if the NCS is fully connected, and then the cooperative DMPC becomes DMPC, and then we have high computation time, which we don't want. What can we do? First, I would like to illustrate this for you. Look at agent A. It's connected with B, C, D, but not with F and E, and B is connected additionally with E and F, but not with D. So the perspective of A is different from the perspective of B, and we will have different opinions leading to different solutions. So hypothetical plans of the agents should be consistent. So again, what I think about you, you think about yourself. This we want to achieve for the whole network. What can we do? In literature in general, they try to solve the optimization problems in sequence and iterate and somehow get to a solution. And one of my PhD students get with the idea of applying synchronization to this problem. What we want to synchronize the plan I am thinking about you with your actual plan. So we are not going to synchronize our actions. We're going also only to synchronize what I am thinking about you with what you think about yourself. So we can use the synchronization for this. So synchronized predictions maybe, but infeasible in non-convex problem. So for convex problem, synchronization solves this problem, but for non-convex, no. So what can we do? We will see in the next slide. And we use the synchronized predictions as references for the next planning step. So we create plans in the first step. In the second step, we synchronize them. You can think of synchronization as computing the mean value of the trajectories. The result in the non-convex space will be not necessarily feasible. So we will use this solution, which is not feasible, as a reference trajectory. Of course, we need to get from there a feasible trajectory, and we repeat this. So we have here two kinds of iterations. And every computer science student will say, talk about the convergence, right? So we have to study the convergence. So looking at this iteration, we can guarantee convergence if the graph is, we prove this, if the graph, synchronization graphs, the single synchronization graphs of every connected part in the undirected variant have a spanning tree, and in the directed variant have an out tree. And how about this iteration, how it converges? So if we can prove if we have local feasibility and global consistency, we can have global feasibility. If the coupling topology is feasible, and coupling topology is feasible, we get out as a result is if the distance between conflicting agents is max 3. And the last theorem says our algorithm will get a solution if the coupling weights are feasible. So the whole idea is about synchronize what I think about you with what you think about yourself. In the simple way, you can think about computing the mean value of both trajectories. And if the solution is not feasible, we can use the solution as a step towards the feasible solution. This is what you can understand from this. How we get to the graph if the graph is not given. So we found in the literature it's used in communication networks to build communication networks. They use game theory, and it's an uncooperative game. The agents are the players, and they have the option to couple or not to couple. And here is the utility function. It consists of conflicting path. So if there is a conflict, the utility is high, they should connect, and a buffer. So if we are going to have a conflict in the future, we increase our utility and the degree. So we want to decrease the degree of connections between the agents to reduce the computation time. So we try to have evenly distributed network or the connections between the agents. So to not have a high degree of connections in one agent and in other agents, small number of connected agents. And of course, of the history, we don't want to continuously change the connections to the other systems. So this was our solution to the cooperative DMPC. There is still work in progress, and we have another solution. It's called the non-cooperative DMPC. So we decompose DMPC again into smaller optimization problems. But the special thing here is we don't optimize for the neighbors. We use their optimized solutions in our optimization problem. So we consider only the objective function and constraints of our cell, and the coupling objectives are constraints with the neighbors coming from the optimization of the neighbors. So computer science students would say it's a greedy algorithm, it's right, it's a greedy algorithm. And we use the communicated optimized predictions from neighbors, and they will be time delayed because they have to communicate their presence. And what happens, it's not prediction consistent in general. I would like to illustrate this with this example. So we place two vehicles symmetrically with respect to the y-axis and let them drive in, so the reference trajectories are the straight lines in each direction, and they drive exactly with the same velocity, of course, in simulation. And if this happens, they are very symmetrically placed around the y-axis. They will collide in the next step, because vehicle one will tell vehicle two, I'm going straight. Vehicle two tells one, I'm also going straight. So each one thinks, I have to avoid the collision, and they avoid each other but to the same direction. This is the pedestrian example. Now you understand the time delay is a cause of this conflict. And again, it's a greedy algorithm. Everyone thinks, the other agent is going to do it. I don't have to do anything. They go to their reference trajectory. And again, and again, and at the end, there is a collision. What can we do? If we look at the coupling graph, it contains cycles between the agents. So we need to break these cycles. And the solution in the literature is, again, in general, solve in sequence and iterate till you get a good solution. It has a high computation time. And I thought we have to bring some organization into the system here and distribute priorities. And depending on the priorities, compute the single BMPCs. So we assign agents priorities. And if we assign the agents priorities, then if we have two agents moving towards each other, one will have the higher priority and one the less priority. And the higher priority agent is allowed to compute first. So priority here is not the same priority, you know, from rules of roads from the street. So it is the computation order and not which agent is allowed to use the space. For doing so, the first agent will compute a trajectory, the second agent will avoid this trajectory, and then we will get to a solution. If the network is time invariant, we are done, and the agents can compute in parallel if they have priorities. If the network is time variant, then we need to compute it sequentially. And again, you can say, now we are getting back to the sequential computations. It takes a lot of time. What can we do? So we're looking at our system, what we get is a partial order. So not every agent is connected to every agent. It's not a total order, it's a partial order. And in computer science, we know we can convert a partial order into a topological order. This is only possible if the graph we created is directed and a cyclic graph, or DAG. And we proved this, what we get distributing the priorities is directed at a cyclic graph. And doing so, we proved, okay, our PDMBC with sequential computations is prediction consistent. So it is prediction consistent only if the solution exists. If a solution doesn't exist, what we can do, we can redistribute the priorities and recompute again. But what if the redistribution of the priorities cannot result in feasible solutions? So we can do something with the recursive feasibility of the system. Recursive feasibility means if we get a solution at a time instant t, we can guarantee that we are going to get a solution at time instant t+1. And we did this, and we showed that we can use the older solution of the MBC under some conditions, and it is recursive feasible. Oh, yeah. And what can we do also? We can reduce the computation time further. Looking at the system, it's this. Maybe I go 2 slides back. So here I showed that we have a topological order. What we can do with the topological order is to put the agents into computation levels. And if 2 agents are independent of each other, they can compute in parallel. So the algorithm we used here to do so, it's called CAN algorithm. So we look at the agent without incoming edges, and this exists in directed acyclic graphs. We delete it, and we delete all the edges out, the outgoing edges, and we look again at the next vertices without incoming edges. We delete them, their outgoing edges, and put them in the next level, and so on. This is how the algorithm works, and we get to our computation levels. This is equivalent, we showed this, to the graph coloring problem. What is the graph coloring problem? If 2 edges are neighbors, they are not allowed to have the same color. And we can use graph coloring. So in graph coloring, we are looking for the minimal number of colors to color a graph. So that means we are looking for, in our case, for the minimal number of computation levels. So we did this, and computer science students know graph coloring problem is NP hard. What can we do? We can use some heuristics to solve it. So we did so, and we get this exciting scenario. Now you may wake up you will see some exciting experiments and simulations. So we are done with the theory. Sorry for the theory part. So on the left-hand side, we see the priorities through graph coloring, and on the right hand side, the priorities with constant distribution of the priorities. And you see there are some congestions here more than on this side. This is because we increase the dependencies between the agents while reducing the computation levels. So we reduce the computation time, but at the same time, we did worse in the quality of the solution. So it is always a trade-off. If you have the same method, it's a trade-off between computation time and quality. And now it's time for you to get active and for me to have a break. Here's a chess game. You are the one playing with the white figures. And I'm asking you for checkmate in 2 moves.
Do not know chess, don't do that way.
So you are playing with the white figures. And you have 2 moves to get checkmate. Please talk about it. Take some seconds to think about it. So, Bert, do you have the solution?
I think I have the solution, Bassam.
This is great. Andreas, tell me the solution.
So I think you move your queen to the left from C3 to B3, and also how do we call this?
The bishop.
The guy from F5 to D3. Yes.
You are brilliant, Andreas. So it is solved and in real time, thanks to Andreas. So Andreas, could you tell us how you got to the solution?
I did the reverse engineering. So I thought, what's the options for the king? And then I eliminated these options by finding the right positions from these guys.
Yes, it's perfect. Why I am showing you this game? First, for me to have a break, to drink something, for you to get you back to this presentation. But this is very similar to our network NPC. So you have rules in the game, you have an objective, you want to win, you have a player you are going to play against. So this is should be conducted in real time. So it's very similar to our game. So if you think again about this, you will understand this too maybe better. If you would like, you can take a picture to think about this more deeply after this presentation. 1, 2, 3, continue. So we applied this not only to vehicles, we applied it also to aerial vehicles. One of my former students applied this.
You can go back to the previous slide. You should have the response of the black. Bishop to D3, what's the black's move?
Anything.
They move A4. A4, right. And why can't it not?
So you mean here? Then it's killed.
Yeah.
Then it's killed.
So, what I mean is that you move the bishop to D3, and then the only move for black is to capture the knight at A4, right?
Here you mean
No. The solution is
to get here.
is correct. Yeah.
Yes. Okay. I hope this is a correct solution. I showed it many times in my talks. I don't know if this is the unique solution. So maybe it's non-convex and we get several minimas. Okay, but this question we can ask to Andreas on Wednesday on Monday in the class. So we applied this to, one of the former students applied this to aerial vehicles. And now I would like to show you some examples we applied in my lab to vehicles. So we have here the crossing scenario. So it's an intersection. Vehicles should drive during the or through the intersection as fast as possible and don't collide with each other. It's a coordination question. And here it's also very exciting. We have the general problem of go-to formation. We have agents we distribute around the place, and we assign each agent a target position and orientation and tell them go there as fast as possible and in real time and don't collide with each other. And we see here the centralized solution and here one of the distributed solutions. And very exciting, the car racing. We applied this also to multiple car racing. The exciting thing about this is, of course, the vehicle shouldn't collide with each other, but they have also to compete at the same time. I want to win also. This is very exciting about this. But to be honest, till now it's simulation. It's a little bit boring. Maybe we need to see something real. And that was our motivation to build the Cyber Physical Mobility Lab. It's something placed between simulation and real world. And the idea of this is to get ideas turning into reality very fast. So here are the features of our lab. From day one, we thought about opening the lab. So everything I'm going to show now is open source, documentation, software, everything. Even we have remote access to the lab. I'll demonstrate the remote access in some minutes. If Armin is in the Zoom call, maybe you can check if he is there. And we allow for centralized and distributed computations, and very important also for computer science students, we have a deterministic computation model. Maybe you have heard about the theories of Professor Lee from Berkeley about the importance of deterministic computations in embedded systems. And if we have deterministic computations, then we have reproducible experiments. And also we have a digital twin of our system, so we can seamlessly extend the number of agents in our system using simulations. So an agent doesn't know if it exists in reality or virtually. Yeah, because of the digital twin. And this is the architecture of the lab. This is the function architecture. We followed the sense plan act scheme, and we have also infrastructure part. In the lab, we focus on coordination and decision making. And yeah, here is our me car. In this letter is mu in English, but in Greek it is me, so it is the me car.
Excellent, excellent. I'm so excited about this clarification.
Thank you, Andreas. So here is our me car, and here are some technical details about it. So we took one out-of-the-shelf car. We equipped it with sensors, IMU, inertial measurement unit. This means the acceleration in three directions. We equipped it with odometer. This is the rotation. It sends the rotation numbers of the wheels. And we have actuators, so servo motor and brushless motor for propulsion. And we have equipped the vehicle with some computations, so mid-level controller and mid and low-level controller. And the high-level controller is logically assigned to the vehicle, but we separated it to the weight because it's heavy for the vehicles to carry during the experiment. So I have also an animation. So we got the parts from off the shelf, and we designed place for the battery, place for the servo, place for the motor. So we designed our system. We designed our PCB, and we put Raspberry Pi 0. W stands for wireless communication. So we need some wireless communications. So here's the IMU, the motor drive, and the microcontroller, the low-level microcontroller. And we have also for the localization of the vehicles, we use LEDs. So we place on every vehicle 4 LEDs, 3 for detecting the pose. Pose is position and orientation. These are the outer LEDs, so pose LEDs. And in the middle, we have an LED blinking in different frequencies to code the ID of the vehicle. So different frequencies means different vehicles. And in the back side, we have Hall effect sensors for the rotations of the wheels. And here's our indoor positioning system. We have a camera placed on the ceiling. It detects the LEDs and computes the position and orientation of the vehicles and also the IDs. So this needs some geometric computations. I'm not going through it. It's some hard work, but not scientifically very interesting. And then after some years of hard work with brilliant students, you get to the code example. We combine theory, application, and experiments. So here in our experiment, we have the intersection. We have highway exits and entrances, or ramps on, ramps off. And we have here some vehicles driving around and coordinating themselves. So the infrastructure part of the lab is more or less done, but some parts we are still maintaining, but as you see, it works. And here's the view from one of the knee cars. So we are now working on a project with our partners from mechanical engineering to study the ergonomy of our systems of autonomous driving in the future. And we place a camera on one of the vehicles to see how it feels to sit in one of the knee cars. So after looking for a while at it, I got busy, so take care while I look at it. And we used that up also in one of our projects with the construction engineers. They want to detect the load of the vehicles on the road, and we found on the market a yoga mat, sensitive yoga mat. We can detect the load of the vehicles while driving on it. This is an ongoing project. And of course, we have the remote access, but I can show you a video, but maybe it's more exciting to go now to Aachen, maybe. So Amin, are you there?
Yes, I'm here.
This is perfect. So
yeah, I'm trying to increase this a little bit. You know, the voice actually controlled by this guy. And ask somebody to say something. Andreas,
okay,
Andreas, can you say something?
Yes, can you hear me?
Oh,
it is.
you need to choose the voice through this guy. Then all of us will hear.
How can I
Go
do
click this one
here?
This microphone. Where's the microphone? Yeah, click this guy.
Okay,
Choose the hour. Can you see hour?
this one. Can you say something?
Can you guys hear me?
Yes.
Then you need to mute yourself. Mute this guy.
Can you hear me now? I have muted myself, so I cannot hear you.
That's interesting.
Okay. And now you can hear me?
Yes.
And is Amin in the Zoom call?
Yes.
Yes, I am.
Okay, perfect, Amin. I'm going now to the CPM website. And now I'm clicking on the remote access. And there you have to register if you are not registered. It's very easy, like ChatGPT. 2 clicks and you are in. And if you are in, you don't get out. So this is the login. I am logging in now. So I got started, so close this. And now I need to create a default project, right, Armin?
Yes,
Yes, and now
central routing maybe.
yes,
I-
central
I-
routing. I'm going to override the project I have now. And now we are using the server in Aachen to build our project. And now it's at 80%. So I hope the server is going. Yes, now we have 100%. And now I can click on the example I chose. It's the central routing. And I can now request a session in the server there. And now I got a session there. And what should I do now? I mean,
Go to session. You need a live session.
yes.
Yeah, go
now-
ahead. Yeah.
Now I'm
So
going to session, and now I have hopefully a live session. Yes, I have a live session. Maybe we can prove this. I mean, maybe you can
Yeah.
show you what.
Maybe you zoom out a little bit so there's more visible.
Like this.
That's fine, I guess. Yeah, you can start.
Okay, can you say hello to the cam?
Yeah, 1 second.
So this is my lab in Aachen, and now we can start the experiment with 3 vehicles. Okay, hello, Armin.
Oh, okay.
So the vehicles are now ready to start. So on the left-hand side, we see the. Okay.
Yeah. We disturbed the indoor positioning system because I went inside. I shouldn't have gone in the middle. Now the vehicles are not visible anymore.
So this is the presentation effect, right?
Yeah, I shouldn't have waved too much. No, you have to kill the session first. Session and then go ahead. Yeah.
So again, end session.
Yes, end the session. Maybe try again. Yeah, go ahead.
Okay. Second try.
The vehicles are gone because I waved too much.
Is it
I
now
can-
going to work?
Yeah, I can restart them real quick. You can end the session.
Okay.
That should be very, very quick. Yeah, end the session. 1 second.
So in the next presentation, I'm not going to ask him to say hello to the crowd.
Okay,
Maybe
the vehicles are restarting right now. So we should give them, you can connect again. This time we won't wave anymore. Okay, they are 1 more second. They are restarting. They click it.
So maybe I come back to you in some minutes.
Yeah, it should be fine.
Okay.
So now the vehicles are, as you see, they are blinking. They are downloading their environment again and installing it on the vehicle itself. And the first one is already visible. There's the second one, and the third one is coming. And if the IPS doesn't get disturbed again, for me, sorry for that, the experiment should work.
Now I can start the session.
Yes, you can start.
Okay, and now I am starting the vehicles from here. Hope they are going to move. Please move my cars. Yes,
Yeah.
they are moving. So thank you very much. I mean, I am now going back to the presentation.
Yeah, not for that.
Yeah, thank you very much. It's now 9 p.m. in the evening in Aachen, so and it's
Yeah.
Friday. So thank you a lot.
You're welcome. See you.
See you. Bye. So I need to do this. So using our remote access, you don't need to install anything on your computer. You can use it directly now. We are going to see it, but I need to move this. Which one? Yes. So now you'll see for the code you can write directly in the browser, and you can look at the editor. So everything is prepared there. You would need just to register, go in, put your code, control the lab. And if you want to have live access to the lab, of course, you have to ask Armin to be there to turn on the lab, but ask him not to say hello to the camera. Yeah, and what we did with the lab, I applied the lab in all levels of teaching, from undergrad to master's to PhD courses. And all are open in the internet. So you can go there and take one of the classes of the undergrad. It's called CPM Academy. You can just go there and learn some C++ programming. You can apply it also in UD in software project. You can go and learn about coordination and control in the master course, or also about control and coordination in the PhD course. And we have a competition, we call it CPM Olympics. In 2 months, in June, we are going to present the first results in a workshop in Alaska, Anchorage, in the IEEE Intelligent Vehicle Symposium. And the next one is coming soon. We are planning one on the CDC, the Conference on Decision and Controls. We are planning a workshop there. We will host our competition. So you can participate and maybe win 1,500 euros. It's a little bit more than $1,500. And we use also the lab for explaining to the public connected and automated vehicles. This is Shari Reeves, one of the famous journalists in Germany, visit our lab and explain autonomous driving using our lab. And we use it also in project meetings to say hello to the cam and put the pictures on the website. And here you see our outreach. We have a lot of visits and downloads from 69 countries in the world. Maybe if you go on vacation to one of the gray countries, maybe you can just access the CPM lab. And what else? We can use the lab also to collaborate. The first collaboration with Andreas was, I said, hey, Andreas, I have a lab like your lab. So Andreas had also a lab like my lab. I saw some of your publications. It's similar to our work. Do we want to talk? It was during COVID, everybody at home. So it was easy to get into a Zoom call, and we started our collaboration. And now I am here. It's a very good idea to build such a lab. And now I talked a lot about connected and automated systems, vehicles, and so on. And sometimes I use the word architecture, and I would like to introduce you to, especially the guys from the mechanical engineering department, to some aspects of architectures. So an architecture means the organization of a system. So this is a building architecture. It should be also beautiful architecture. So it describes the components of the system and the interactions between the components. So this is something what we have now in road vehicles. So this is something rigid. What we rather want to have is something like this, something dynamic, something modular, maintainable, updatable, all the passwords you have here also from Tesla. And this is an example showing today's architecture. So I'll explain it using the Sales Plan Act. So each function is mapped to a software part. The software is mapped to ECUs. There are dependencies between the software parts. And if we want to update some trajectory planning, we have to update all the software parts connected to this. Our solution, what we came up with, is service-oriented software architecture. It's a better organization of the system, and it's for software-defined vehicles. So software-defined vehicles means we start our development of the vehicle looking at the software, not at the hardware. So we organize the system into different levels. So here we have our operating mode, so autonomous driving, safe halt, or remote operation. So if the vehicle gets into a deadlock while driving autonomously, we can switch to remote operation, where a human operator can get the vehicle out of this. And here's the function architecture. This is only an example, right? So we have here Sales Plan Act, and they are mapped to services, and the services are mapped to ECUs. This is a very short introduction into architecture. And now we are switching from autonomous driving into remote operation. And this is what an architecture should enable. It should ease the organization of a system. And we have built a whole pipeline about this, and we applied this in a big project with 100 researchers, and applied it to 4 vehicles. We see 3 of them here, and we built these vehicles from scratch, completely, software and hardware and everything, within 5 years. And now the vehicles are driving. So here are some videos of the vehicles, and the final event of the project is going to be in 1 month. So all 4 vehicles will be able to move autonomously, hopefully. And what else? What's exciting about architectures in control? So we are now studying this to have an architecture for our control system to explore what can we do with this in control. So what can we do? We can, for example, have several models, several controllers, depending on the mode of the system. We can connect them and so on. This will create some effects we are going to handle. And here again, a video. So we are going now in a project where we are collecting data about dangerous situations. Look at the skid mark of this vehicle. So while braking here to take care of the cyclist. And here also a further example where we are collecting data to see how we can improve the interaction between connected and autonomous vehicles and humans in general, not only human-driven vehicles with cyclists and so on. Here you see how the cyclists say, this is my lane, go out of it. So what I have shown, distributed MPC applied to connected and automated vehicles, and I showed the experiments. What are the challenges in the next years? We are dealing with mixed systems, data-enabled or driven systems, software-defined systems are challenges. Of course, always reducing computation communication, increasing efficiency of time and energy, improving safety and optimality, and we need tools and further applications. So I would like to thank my team members for contributing to all this work, and thank you for your attention. And now I'm very happy to discuss with you. Questions?
Hello?
Oh, okay.
Go ahead, maybe online guys do first.
Yeah, hi, Professor. I think your work is very interesting. And I have a question about the demo you showed in the lab. So I was wondering how the car do the localization in the real demonstration. Is that based on camera or something else? Thank you.
Yeah, thank you for the question. In the lab, we used a camera mounted on the ceiling to detect the vehicles. So we detect the LEDs, the 3 outer LEDs for the pose and the middle LED for the ID of the vehicle. But this is only in the lab. So in the lab also we have a simulation of the reality. So we take this position and disturb it and get a GPS position out of it. And then we can also fuse the GPS position as in reality with the sensors of the vehicle, with the IMU and the rotations of the vehicle. And also you can add more and more sensors. So this is ongoing work in the lab. Now we have the infrastructure part of the lab, and now we are looking on how we can simulate some parts of the reality in the lab. So the GPS part we did already, so we can simulate GPS in the lab, so we can put some soft GPS satellites in the lab. Does it answer your question?
Thank you. Actually, I have another question about the waypoints. I saw the waypoints in the simulation, so I was wondering, is the waypoints is predefined or the waypoints can be generated dynamically in the online planning or real world? Thank you. That's my last question. Yeah.
Yes, welcome. So the waypoints you saw are the predictions of the MPC, the optimized predictions of the MPC, and these are sampled. So the distance between them depends on the velocity, speed, and on the sample time. And of course, we have a horizon. So the waypoints you saw, they are inside the prediction horizon I showed at the beginning of the presentation. So I hope this is the answer of your question.
Thank you. Thank you.
Mike.
Good, yeah, he's my student anyway, so he is asking questions from our lab. I have a question on that. This is, first of all, this is fantastic. Okay, this is really cool. But from your lab's name, I can tell human is not here. So tell me your whole simulation, have you consider if there's some pedestrians, for example, if the people is moving, so what the simulation will look like?
Yeah, in the lab, of course, we have the digital twin. We can use it to extend the lab. So we don't have humanoids, but maybe Abby can build some of them. So this guy is working with Professor Polakakis in mechanical engineering on humanoids. So I think both of the guys there. So maybe we can get some robots there to simulate pedestrians, but we can do so also in the digital twin. And actually, we did this in our competition in CBM Olympics. So some parts don't exist really physically in the lab; they exist only as digits in a digital twin.
So your vehicle, in the digital twin, what's the mechanism used for your vehicle to detect there's a human in front of it?
Okay, we assume that we know the position and orientation of the human, of course. This is not the, yes, totally right. This is not the focus in this lab. We focus on coordination and control and not on perception. But the perception part is very interesting. So maybe we will have some work on this in the future.
Yeah, I will come to you later. So I let them ask the questions. I didn't talk to a guy right now. Okay.
Also, of course.
Yeah, I was. She has just bring him to my office. Okay.
Okay.
See you.
Okay. See you.
Question. In the very last part of your presentation, you mentioned that you have also like some operator who take over the control of the vehicle if the situation needs that.
Yeah.
to be done. My question is, how do you integrate that with the control system? It's like shutting off the control system and then the car has all the equipment for a human to drive it, or how do you handle this?
Yes, the human operator is sitting in an operation center and gets a video stream from the car. So this is not our work in this project. Our partners do this. The human operator looks at the screen and see the front camera and the back camera and so on the screen. And what we do, we switch between autonomous and remote operation. And in the remote operation, we switch off some of the services. The services you can think of software parts. So we switch off some of them, and the human now is allowed to take action in the car. But in my lab, we have two modes of operation. The human can directly change the steering angle, or the human can tell the vehicle the X and Y coordinates where to drive. For X and Y, you have to compute in the remote part, right? But if you want to get a vehicle out of the deadlock, then you need to drive from the remote. It's similar to the operator in the city, but in reality, this place is going to be separated, of course, from the road. And in some centers, some people will sit and take care of the vehicles which are in the road.
Okay, like a follow-up question that I
Yes.
have. Is the vehicle decision to do the switching between the two types of operation, or the human can just decide to take over the control?
No, in our case, we decided that the vehicle should be big. Okay, I am in trouble. And this we call self-awareness. So the vehicle should feel itself continuously. And if it detects there is a problem, then the vehicle should drive to a safe house, we call it. So the vehicle computes always from each state, not only the trajectory it's going to drive, but also a safe trajectory to going to a house. And if it gets there and doesn't know how to continue, because maybe assume the vehicle is standing in front of a pedestrian walking, and pedestrians are standing there. I want to cross, but they don't cross. So they are just standing there. So the vehicle by law is not allowed to cross the pedestrian walking, but the pedestrians will stay there. So what to do? Maybe the pedestrians are showing to the vehicle, drive, I have time, but the vehicle doesn't drive. So it is a solution to get back to the operating room, and then the human operator can slowly drive the vehicle and look and maybe say hello to the pedestrians. Look away, we have to drive.
Okay.
Something like this.
Thank you so much.
Welcome.
So we have a question from the audience. William has a question about the controls in the digital twin. So do you consider the real-time controlling for the small robots?
Yes. So real time, of course, depends on how you define real time, how you define the time, the sample time within it. The computations should be done, and this sample time depends on many things. It depends also on the speed of the vehicle. So you can imagine between the sample times you have dark spots, so you don't see between the sampling time. So you sample again and again. And our implementation of the distributed MPC, we could solve it on NUCs. So NUC, Intel NUCs, maybe you know this. so small computers. So within several hundred milliseconds, I don't remember exactly, something between 200 and 400 milliseconds. And people say for autonomous driving, you should have 200 milliseconds sample time and a prediction of 10 seconds. And I think this is doable using our centralized architectures where we, of course, on the one hand, you can say, in reality, the vehicles have limited computation power on the road, but we are researchers, so we are looking towards the future, and we are looking towards more computation power. And our architecture, the service-oriented architecture, allows to centralize the architecture, to not have a lot of ECUs in the vehicle, but some maybe 4 or 5 computers with high computation power, and then we can use them also to reduce our sample time and to compute heavy computations. So this is the vision, and this is what we implemented in the project, in the real world project, the Unica Ideal project. We have there 5 high-level computers, 4 for the sensors. On each corner, we have sensors and computers to compute the image stream, the laser stream, so the laser beam stream, the radar streams, and so on. And we have in the middle, in the architecture, of course, a high-level computer which computes the high-level trajectory planning and stuff like this. I hope this answers your question from the audience.
I have 2 more questions.
Yes, of course.
So you just showed us 2 video clips that the car almost hit a bicycle, right? Is that an autonomous driving car or car driven by a real person?
These cars are driven by real persons. And the goal of this project is first to collect data. And what we are going to do in this project is to provide an app and ask the people in our city to install this app and to activate it while cycling. And then we will collect data. And we will give this app also to car drivers and ask them also to activate it while driving. And then we will also collect data. And from the data we are going to collect, we are going to identify dangerous situations or dangerous corners and say, okay, this corner in our city, the 2 corners were shown in the video. I know both of them, and I know they are dangerous spots, so you have to take care while cycling there. And in the first step, we are going just to say to create a map where we say this is a dangerous spot. Actually, the first part of the project, or a part of the project study, is already done. I can show you. So you can go to this website and you can search for the dangerous So here in this spot, we identified more than 1,000 and so on dangerous spots. So, and classified them. And in the future, we are going to use them to for the interaction between connected automated vehicles and human-driven vehicles. But first, we are just identifying dangerous spots.
So last question. So
yes,
in the one example, our first example, the 0 to 100 example, you ask us to choose the numbers. If you think 1 wrong, the answer will be 50. Right? If you think 2 wrong, it will be 25. And if it's in one more round, it will be 12.5. And you say if you keep going, finally when you reach the Nash equilibrium, it will be 0. So, but in the CFA, to avoid collision, you don't need to reach the equilibrium, right?
You will need a feasible solution in the vehicles.
Yeah, so I mean, just in a couple of rounds to avoid the same decision on different cars.
Yes, we need to get to feasible solutions. Actually, this game is only to get you into the network thinking. It's not related to the vehicles. It's only to activate your participation in this presentation and to get you into the network thinking, because it's not always easy for people to get into network thinking. What I think, what you think, and you can extend this, what you think about him and he about him, and maybe you can take a picture. Why I am so excited. Thank you.
Okay, so can I ask the last question?
Of course.
When you saw the distributed MVC, you have some kind of algorithm to reduce the computation and communication expand of the controller. So my question is that can you guarantee the optimality of the MVC problem compared to when you solve the problem in centralized manner? So what is the gap between these two kind of controllers?
Yes, of course, there is a gap. This is a very good question. So when we evaluate our scenarios, we take the objective value of the distributed MVC and divide by the objective value of the centralized MVC and show it in different scenarios. So it's not always, of course, the same. It depends on the scenario, on the computation method, on the levels of computation. Let me give you an example. If we choose constant priorities, then this gap is smaller than if we use the coloring. Why? Because while we use the coloring, we reduce the levels of computation as much as possible, but we increase the dependencies between the vehicles. So we are increasing the dependencies, so the gap is going to be bigger and bigger. So guarantee for feasible solutions doesn't exist, because we have here to deal with distributed, non-convex, non-linear systems. So there is no guarantee. And what can we do in case of infeasibility? We can go to an invariant set. So always define a backup trajectory which is feasible. For example, this could be, maybe you know also this example. You can compute always a state of the vehicle in which the vehicle is standing. But this is not always safe, because somebody can come from behind and crash into the car. But in general, if you can control the whole system, you can try to compute invariances. Yeah. So this is somehow a general answer.
Yeah, thank you.
Are they right?
Yes, thank you. Thank you.
Nice presentation, Bassam. I'll see you on Monday.
Yeah, thank you very much, Andrea. See you on Monday.
Bye-bye.